So start over. All right, so here's a question that is easily solved using the idea of moles of reaction. Okay, so you have, in this problem, you start off with 1 mole of H2 and 1.5 moles of N2, and the reaction according to the problem will involve 3 moles of H2 for every mole of N2 to give you 2 moles of NH3. Okay, so initially according to this, you have 1 mole of H2, 1.5 moles of N2, and 0 moles of NH3. All right. Now, if we say that we have X moles of reaction, then the changes will be related by their coefficient. So we say that we're going to lose 3x moles of H2 since the coefficient of H2 is 3. We are going to lose x moles of N2 because the coefficient of N2 is 1. And we're going to form 2x moles of NH3 because the coefficient of NH3 is 2. Okay, so if you have x moles of reaction, you're going to lose 3x moles of H2, 1 mole of N2, and 1x moles of N2, and 2x moles of NH3. So you'll end up with, okay, if 1 mole of H2 is what you start with and you lose 3x moles, you end up with 1.00 minus 3x moles. Okay, starting amount minus the amount that was lost would leave you with 1 minus 3x. N2, you start off with 1.50, you lose x moles, so 1.50 minus x, okay? And NH3, you start with nothing, so 0, and you end up, and you gain 2x moles, right? Now, according to this problem, sometime later, you have 2.30 moles of gas molecules were found. So what would those, that would be the total. Now, if you look at your balance equation right here, according to this balance equation, H2 is a gas, nitrogen is a gas, ammonia is a gas. So if you add up the ending moles, then you're going to get, according to this, 2.30 moles of gas. So what do we do here? We say 1.00 minus 3x plus 1.50 minus x plus 2x must be equal to 2.30. Okay, so the ending moles add up to 2.30. And let's combine this. This is going to be 1 plus 1.5. That was the problem I had earlier. I put 3.5 there. That should only be 2.5. Okay, negative x and negative 3x and negative x is negative 4x, okay, plus 2x is equal to 2.30. So you have to be careful with your algebra here. So 2.50, negative 4x and 2x would be negative 2x equal to 2.30. Okay. Subtract 2.50 from both sides, so negative 2x would be equal to 2.30 minus 2.50. Divide both sides by negative 2. Let me just rewrite this. Negative 2x, so this is 2.3 minus 2.5, that's 2.2, right? Negative 0.20. Correct number of sig figs there. And divide both sides by negative 2, so you say x equals negative 0.20 divided by 2. So x is equal to 0.2 divided by 2 is 0.1. This should be divided by negative 2, so that should give you 0.10 moles. Okay, so this is your moles of reaction. Okay, so going back, you're going to say H2, you have start off with 1 minus 3x. That will leave you with how much? So for H2, so your ending moles would be, for H2, you have, how much did we say we have? 1 1.00 minus 3x. So that's going to be 1.00 minus 3 times 0.10. So that's 1.00 minus 0.30 or 0.70 moles. So moles H2 left is 0.70 moles. Okay? How many moles of nitrogen would you have left? You'd have 1.50 minus X. So ending moles for nitrogen is 1.50 minus X. So that's 1.50 minus 0.10. That gives you 1.40 moles of nitrogen left. Moles H2, N2 left would be 1.4. And how much NH3 would you have made? According to this, you end up with the original amount, which was 0 plus 2x. You'll end up with 2x moles of NH3. So for NH3, you have 2x moles formed. And so you end up with 2 times 0.10 or 0.20 moles. Okay? So let's verify that these numbers actually do add up to 2.3. So you'd have 0.7 plus 1.4. So for H2 you have 0.7. Nitrogen is 1.40. And NH3 you have 0.20. So that would be 0.7 plus 1.4 plus 0.2. That gives you 2.30 moles. So we get the right numbers. Okay? So this is known as the ICE table approach to solving stoichiometry problems. This is particularly useful sometimes when a straightforward use of conversion factors will not work. Because here you're not told how much reactant or product was consumed. Okay, you were just told how much you have in the end, so you kind of have to figure out how much the change was to begin with. Okay, so that's how you use an ICE table. All right, so one thing you realize here is that when you have a reaction, it doesn't necessarily mean that you're going to lose all of your reactants. You might have chances, most likely, you're going to have some reactants left behind after the reaction has occurred. Okay, in fact, it's not necessary for any of the reactants to be completely consumed during a reaction. So let's talk about the concept now of a limiting reactant. A limiting reactant, okay, is defined as the reactant that puts a limit to the amount of product you can gain from a reaction. And so the limiting reactant of a reaction is the one that would be used up first. It's not necessarily going to be used up, but based on the amounts that you have to begin with, that would be the one that would be used up first. Okay? So, and it's not necessarily the reactant that you have a smaller amount of. Okay? Now, the theoretical yield is the limit. How much product, what's the maximum amount of product that you can get? So that's the amount that you would get if the limiting reactant were actually consumed completely. So, like I said, that may not be what you'll get. So the actual yield, the actual amount of product you have, divide that by your theoretical yield, multiply by 100%, that gives you what you call your percent yield. Let me just illustrate that with a simple example about making sandwiches, just to make things a little easier to visualize. Let's say you have, okay, so the formula for a sandwich, a cheese sandwich would be 1 piece of cheese plus 2 slices of bread would give you a sandwich. So what's our formula for a sandwich? 2 slices of bread and a slice of cheese, okay? So let's say you've got, okay, let's see. Let's say you have 4 slices of cheese, okay? So Swiss cheese. and you have 4 slices of bread. Wonder bread, right here. Okay. How many sandwiches can you make? What's the most number of sandwiches you can make? Well, let's see. 2 slices of bread and 1 slice of cheese would give you 1 sandwich. Okay, 2 slices of bread and 1 slice of cheese would give you another sandwich. That gives you 2 sandwiches, right? So your theoretical yield is 2 sandwiches. Okay? So what ingredient will you run out first? You'd run out of your bread first, so you say your bread is your limiting ingredient. So that's your limiting ingredient. So if this was a reaction, chemical reaction, B would be your limiting reactant. That's the one you'd run out first based on how much you have to begin with. Okay, notice that you have 4 slices of cheese and 4 slices of bread. Although you have equal amounts of bread and cheese, you'd run out of bread first. So your bread is your limiting reactant, your limiting ingredient. Okay? Only 2 slices of cheese would be needed to make the sandwiches. By the time you've made 2 sandwiches, by the time you've gotten your theoretical yield, you're out of bread. Okay? So your cheese in this case, right? Your cheese in this case would be your excess reactant. Okay, your excess ingredient. So the amount of product, the amount of sandwiches you can make is limited by the amount of bread that you have. So how would I solve for this problem if I were to set this up using like a conversion factor? I'm going to say, based on my limiting reactant, 4 slices of bread times 1 sandwich for 2 slices of bread would only give me 2 sandwiches. So this is my theoretical yield. Okay? Now, what if I'm not hungry? I just made one. I've got 4 slices of bread in the kitchen and 4 slices of cheese, but I'm not hungry. I just want to make 1 sandwich. So my actual yield, okay, so you say, what if I only made 1 sandwich? Then I'm going to say my actual yield is 1 sandwich, B2C. But my theoretical yield, based on how much I have, I could have made 2 sandwiches. So I would then say that my percent yield is 1 out of 2, right? 1 B2C out of 2 possible B2Cs times 100%. 1 out of 2 is 50%. So that's the idea. In general, when you run reactions in the lab, you mix 2 or more reactants. One of those reactants is most likely going to be controlling how much product you'll get. So that would be called your limiting reactant. That's the one that would run out first. It might not actually run out first, so you're not going to get 100% yield. Okay? So let's look at an example here. Let's say you have 2 grams of X. It's completely used up when it combines with Y. So X plus excess Y gives you Z. And you have 2 grams of X and you got 18 grams of Z. Right? Whereas if you start off with excess X, okay, plus 4 grams of Y, you get 4.5 grams of Z. Okay? The question here is, what would be the limiting reactant if I were instead going to mix 2 grams of X and 4 grams of Y? How much Z can I get? What's my theoretical yield? And what's my limiting reactant? Let's take a look at this. By the time you make 4.5 grams of Z, okay, all of this 4 grams would be gone, right? So according to this, it's not possible to make more than 4.5 grams of Z because you only have 4 grams of Y. Okay? But according to this, if I had 2 grams of X, I can make as much as 18 grams of Z. So that means I can make more than 4.5 if I were to be able to use up my X. But by the time I make 4.5 grams, I'm out of Y. So I can either make 4.5 or 18, but 18 is impossible. 4.5 is what I'll make, because by the time I make that 4.5, all of my Y is gone. So your limiting reactant here is your Y. And your theoretical yield will only be 4.5 grams of Z. Okay? By the time I make my 4.5 grams of Z, I'll be out of my Y. And I can actually figure out by proportion how much of my 2 grams of X would have been used up. I'm not going to use up all of that 2, because if I were to use all of that up, I'd make 18. I cannot make 18. I can only make 4.5. Just like over here when we said with the bread example, okay? 4 slices of cheese would give you 2 sandwiches. 4 slices of bread would give you 2 sandwiches, whereas 4 slices of cheese would make you 4 sandwiches. By the time you've made 2 sandwiches, you're out of bread. Okay? So by the time you've reached your theoretical yield, you're out of your limiting reactant. You still have some cheese left over. So let's look at an example here. Another example. Let's say you have this reaction, 2H2 plus O2 gives you H2O. Let's say you were to mix 3 moles of H2 and 2 moles of O2. Let's verify that H2 is in fact the limiting reactant. So how would we do that? Well, let's assume, okay, since we're assuming H2 is the limiting reactant, okay, so let's assume H2 is the limiting reactant, and let's do calculations to verify how much of the changes others would change, right? And based on those changes, see if that's a reasonable assumption. Okay, so assume H2 is the limiting reactant, and then you're going to say, all right, 3 moles H2 will consume, according to this balance equation, the H2 to O2 ratio is 2:1. So it's going to consume 1 mole of O2 for every 2 moles of H2. Okay? And that gives you how much? 3 times 1 divided by 2, 1.5. 1.5 mole of O2. This is consumed, right? Do we have enough O2 then? Well, according to this, you start off with 2 moles of O2. So that means 2.0 moles O2 to start with, minus 1.5 moles of O2 consumed. That leaves us with 0.5 moles O2 unreacted. So our assumption is correct, okay? That in fact H2 will be consumed first. By the time you lose your 3 moles of H2, you would have only lost 1.5 moles of oxygen. So since you start off with 2 moles of oxygen, you'll still have half a mole of oxygen left over. So we just verify that H2 is the limiting reactant, okay? if you were to make the opposite assumption, if you assume that O2 was the limiting reactant, you'll find that you'll end up with a negative amount of H2. Okay, so we figured out how much O2 will remain unreacted by the time H2 runs out. What's our theoretical yield? Well, our theoretical yield is the yield we get, the amount of product you get if all of the H2 were used up. So if we assume 3 moles of H2 were used up, okay, you can predict how much water can you make. Our product ratio is, product to reactant ratio is 2:2. 2 moles water for 2 moles of H2. So you can say times 2 moles H2O over 2 moles H2. And that would give you 3.0 moles of H2O. And this is your theoretical yield. That's how much water you can make. That's the most you can make from this reaction. You can't make any more. By the time you make that much, all your H2 will be gone. So that's your theoretical yield. You may not make that much, okay? So your actual yield may be less than that. All right, so that's how you figure out your theoretical yield. If you want that in grams, you can always change moles to grams. Now, what if we made the assumption, the opposite assumption? Okay. What if we assume the opposite? Let's see what happens. If we made the opposite assumption, let's do this. Okay. What if, so if we assume O2 is the limiting reactant, then you're going to say, all right, I'm going to lose all of those 2 moles of O2. Let's figure out how much hydrogen I'll lose. Then I'll say, according to the balance equation, the oxygen to hydrogen ratio is 2:1, right? So 2 moles H2 for 1 mole of O2 according to the balance equation. There's 2 right there and there's 1 there. So that gives you 4 moles of H2 used up. So if you were to use up 2 moles of H2, that would mean you also use up 4 moles of H2. But according to the problem, you only have 3 moles of H2. So this is impossible. So the assumption is wrong. Okay? You cannot use up 4 moles of H2 because you only have 3 moles to begin with. It's like saying from the 4 slices of cheese earlier and the 4 slices of bread, you know, the 4 slices of cheese will give you 4 sandwiches, but by the time you make to make 4 sandwiches, you're going to need 8 slices of bread. You don't have enough bread. Okay? All right, so this is an impossible situation. So in other words, when you're solving stoichiometry problems, if you're given the starting amount of reactants, 2 or more reactants, you have to figure out first which one is the limiting reactant in order to predict what's the maximum amount of product you can get. That maximum amount you can get is called the theoretical yield. Okay? So here's a strategy then for determining the excess reactant. Assume one reactant is the the limiting reactant. So assume one reactant is the limiting reactant. It's completely used up. Calculate how much of the other reactant is used up and subtract from the initial amount. And as we've said earlier, if that turns out to be negative, your assumption is wrong. So going back here, okay, impossible. Why is this thing impossible? Because then you'd say 3 moles of H2 to start with, right, in this question right here, in this example, 3 moles of H2 starting. You lose 4 moles of H2 if all the O2 were used up. you end up with a negative 1 mole of H2. You cannot have negative amounts of substances. Okay, so like I said, this is an incorrect assumption, and that's why you end up with a negative moles of H2 here. Okay, so that's one strategy you can use for determining excess reactant. If your assumption is wrong, then make the opposite assumption to get the right answer. One strategy you can use, if the question is just asking you for a theoretical yield, one quick strategy you can use for quickly getting to the answer is assume one reactant is limiting, calculate the theoretical yield. Then assume the other reactant is limiting, then calculate the theoretical yield. Whichever assumption gives you a smaller theoretical yield, that would be the correct assumption. Why? Because by the time you get that smaller amount, one of the reactants would be completely consumed. It's not possible to get the larger amount. Okay? So that's similar to the example we had, the fictitious example we had earlier about the X, Y, and Z. This one, right? No, not that one. This one. Okay? So according to this, the theoretical yield for 2 grams of X is 18 grams. The theoretical yield, if 4 grams of Y is consumed, is 4.5 grams. So the smaller of these two theoretical yields would be the correct theoretical yield. Okay. So that's one way of doing it. Let's try this example again using that H2 plus O2 example. Okay. So if you have H2, 2H2 plus O2 gives you 2H2O. Let's say you start with, how much was it we had earlier? Three moles and 2 moles. Okay. Three moles of H2 and 2 moles of O2. Okay. So from 3 moles of H2, I can predict how much water I can make times 2 moles H2O over 2 moles H2. Okay. So this 2 is to 2, 2 is to 2. That will give me 3 moles of H2O. All right, moles H2 cancels. But if I had 2 moles of O2 consumed, what's the mole-to-mole ratio of water to O2? It's 2 is to 1. So 2 moles H2O for 1 mole of O2. Okay, 2 is to 1. That gives me 4.0 moles of H2O. Clearly, by the time I use up my 3 moles of H2, I would have made 3 moles of water. I can't make any more, right? So this is not possible. So 3 moles of H2O is your theoretical yield. That's how you figure out theoretical yield. Okay? So you can also use an ice table for doing this. So you'd set up like in that example we have. Let me see if I have that example. Here's another example we can try. This time using an ice table. Okay. So the strategy for using ice table is you assume one reactant is limiting, and you calculate the ending moles of the reactant. Okay, all the reactants if your limiting reactant is consumed completely. And if you get a negative number, your assumption is wrong, and so you go back and try the other assumption. So let's look at this one. Consider a mixture of 0.6 moles H2, 1 mole of N2, and then you're asked to determine the theoretical yield and the amount of excess reactant if the reaction were to go to completion. Okay? So we're going to lose 3x moles of H2. So you end up with, this should be 0.600 minus 3x. Okay. And you're going to lose x moles of N2. So you'll end up with 1.000 minus x. And you're going to make, according to this, 2x moles of NH3. So you end up with 2x moles of NH3. 0 plus 2x, which is just 2x. All right? So you can assume H2 is limiting. Then you say, then 3x must be equal to 0.6. Okay, in other words, if you use up your H2, okay, you're going to say, all right, 0.600 minus 3x must be equal to 0 if it's limiting. It's the one that would run out. So what if it were to run out? How would you solve for x? So you have negative 3x equals negative 0.600. Solve for x. X equals positive 0.200. Okay? Then how much N2 would you have left? You start off with 1, you lose x. So 1.000 minus 0.200. Oops. You have 0.800 moles left. So that assumption is correct. H2 is the limiting reactant. By the time you've lost all of your H2, okay, you still have 0.8 moles of N2 left. If you made the opposite assumption, then you're going to get a negative number. So what's your theoretical yield here? NH3 yield, theoretical yield would be 2x. So that's 2 times 0.200. NH3 has a coefficient of 2, right? 2. So 2x. So that gives you 2x would be equal to 0.400 moles of NH3. Okay? That's your theoretical yield. Now, what if you made the opposite assumption? Let's say, assume N2 is the limiting reactant. Then you're going to say, then you'll end up with no N2, right? So 1 minus x, you're going to say, the amount of N2 will end up being 0. So 1 minus x is going to be equal to 0. So you say 1.000 minus x is going to be equal to 0. So x must be equal to 1.00 moles. And so you can say, if that's the case, then the H2 that's left would be, what was the amount left of H2? 0.6 minus 3x. 0.600 minus 3 times 1.00. That's going to be negative 2.400 moles. Okay, so that negative number right there tells you that this assumption is wrong. So this is the wrong assumption. Okay, so that's the idea behind limiting reactants. Okay, like I said, you generally don't expect to get 100% yield from reactions in the lab, and so if we does go to 100%, we say the reaction goes to completion. So reaction generally does not go to completion. Your limiting the reason could be that your limiting reactant is not used up, and sometime later in your lessons in chemistry, you'll learn that reactions are in fact reversible. So products could recombine, react to give you back your reactants. So you reach a point where you have what's called chemical equilibrium. Okay, so generally, strictly speaking, there's really no reaction that's 100% complete, but some reactions do go far enough to the right, so you can say they essentially go to completion. And then if you're doing things in the lab, you may not get your 100% yield, because if you're trying to recover the product because you're trying to make something that you want to use for something, you may lose some of that during the recovery process. Now, one way you can improve the percent yield, and you learn why this works when we get to this lesson on chemical equilibrium, is you can use a very large excess of one reactant. And this is useful if you're trying to make something. What you want to make as your excess reactant is the one that's very cheap, and so you want to, that would ensure that the more expensive material will be completely converted to whatever you want to make it into. Okay. So percent yield. Let's look at this example. Let's say you have a hypothetical reaction here. 2A plus 2 moles of A plus a mole of B gives you C. Let's say 0.3 moles of A and 0.2 moles of B were allowed to react, but only 0.12 moles of C was produced. Calculate the percent yield. So if you want to know the percent yield, then you have to have the actual yield divided by the theoretical yield. Okay, so this question tells you the actual yield. So your actual yield is 0.120 moles of C. So you have to figure out your theoretical yield in order for you to calculate the percent yield. And of course, this is to be expressed as a percentage, so you multiply this by 100%. So the question then reduces to ends up being a question of finding out what the theoretical yield is. So you have 0.3 moles of A, 0.2 moles of B. So what would you do? You'd say, okay, I have 0.3 moles of A. How much product can I get? According to this, the C to A ratio is 1:2. So I can make 1 mole of C from 2 moles of A. So that gives you 0.3 divided by 2 is 0.15 moles of C. If A is my limiting reactant, okay? So if A is the limiting reactant, you get 0.15 moles of C. What if B is the limiting reactant? Then you're going to say, how many moles of B do you have? 0.2 moles of B is the amount you start with. So you say 0.200 moles of B times 1 mole of C comes from 1 mole of B. 1:1 ratio according to the balance equation. So that's going to give you 0.200 moles of C. Okay, remember we said earlier, you make two assumptions about what the limiting reactant is. The one that gives you a smaller theoretical yield is the one that gives you the correct theoretical yield. So this is the correct assumption. This is the correct theoretical yield. By the time you make 0.15 moles of C, all of the A would be gone. You cannot make more than that. Okay? So your theoretical yield is 0.15. So this is 0.15 moles of C. So 0.12 divided by 0.15, our percent yield is 0.120 moles of C over 0.150 moles of C times 100%. Okay, that is equal to 12 divided by 15, 80% yield. 80.0%. Okay, so that's how you calculate your percent yield. Compare the actual yield to your theoretical yield. Okay, so here's a pictorial representation of a reaction. Let's see if you can identify the limiting reactant here. First of all, what's this reaction? You got H2. 1, 2, 3, 4 H2s here. Okay, on the left. And on the right, how many H2s do you have? You have no H2 here, right? And what else do we have here? you have N oxygen. There's 1, 2, 3, 4, 5 O2s on the left. And here you have 1, 2, so 3. So that means 5 minus 3, 2 moles of O2 used up, right? And I have all four molecules of H2 are used up. So H2 and O2 are both reactants. What else do we have here? You have this one right here, H2O, H2O. 2 on the left, and on the right you have 1, 2, 3, 4, 5, 6. So from 2 you end up with 6, so you have 6 water molecules formed. Okay, and what else do we have here? Your N2. This is N2, nitrogen. 1, 2, 3. 1, 2, 3. So N2 is a spectator. It's not involved, right? All right, so let's do a clicker question here. Which of these, A, B, C, A, hydrogen, B, O2, or C, water, is the limiting reactant? Which one is the limiting reactant? A, B, or C? Okay, the limiting reactant is the reactant that would be used up first. So it can't be, and it's a reactant, so it can't be C, right? And which one is in fact used up first here? H2. You don't have any H2 in the after picture. So the correct answer is A. H2 is your limiting reactant. You don't have any H2s left. You still have, from 5 O2s, you still have 3 O2s left on the right. The correct answer is A. All right. Here's a series of experiments, 1, 2, 3, and 4. You react solution A with 1 ml of solution B. Okay, so solution B, you have 1 ml in each of these experiments. You vary the volume of solution A. The reaction goes to completion, and you produce a gaseous product C, and the volume of the product obtained is shown in this graph. So experiment 1, experiment 2, 3, 4, 5. What's the limiting reactant in this experiment, in each experiment? Now, if the way you interpret this graph right here, look at this part right here. In these experiments, okay, the amount of product depends on the concentration, the amount of A. So we say A is the limiting reactant. The more A you have, the more product you're making. Okay? So that means A is your limiting reactant. A controls how much product you make. But this part of the experiment right here, from 3, 4, and 5, okay, amount of product does not depend on A. Okay, so A is not the limiting reactant here. Whereas here, A is the limiting reactant. Remember, we said the limiting reactant is the reactant that controls how much product you can make. It puts a limit on the amount of product you can make. Okay, so that's the end for stoichiometry. So let me stop recording.